Good day. There are various kinds of materials in nature, and they fall into several different categories. For example, you can have strictly elastic types of materials, and this is exemplified by this spring right here. You stretch it, and it tends to come back to its original shape. Elastic materials are quite common in nature. Of course, we make lots of manufactured elastic materials. And when you talk about things like biomechanics, how bones stand up to strains and those kinds of things, then elastic types of materials are predominant there. But there are lots of other different kinds of materials, specifically fluids. Fluids include things like air and water, and nearly every living thing on Earth lives in some kind of a fluid environment. Furthermore, virtually every living thing on Earth is made up of quite a lot of fluid, and either air or mostly water in the case of most organisms. So in terms of not only understanding how organisms hold up, but also how they interact with the environment, we have to understand something about how fluids behave and the different kinds of fluids that there are and some of their fluid properties. Okay, now when we talk about, if we go back to our spring right here, the main thing that that characterizes this as an elastic material is that when I stretch the spring, like this, I'm doing work on it, but then that work can be tapped to return the spring to its original shape. This tendency to snap back to an original shape is a very characteristic of an elastic material. And there are lots of elastic biological materials out there. We've spoken about some in other videos in this series, bone, tendon, those sorts of things. But water itself, if it's treated the right way, can actually behave as an elastic material itself. Now, we can demonstrate this quite nicely by just cooking up a batch of Jell-O in our kitchen and letting it set. And if we turn to the batch of Jell-O, strawberry Jell-O that I made up last night, here it is right here in front of me. I hoped that it would be a nice square, but it turned out to be more of a blob, but that will work for us just as well. Now, if you look at this, the Jell-O is holding up in terms of in its shape, so it has some integrity, just like our spring does. And if you move it back and forth, like I'm doing right now, you can see that it is subject to elastic deformations. It keeps going for a while, but after it stops sloshing back and forth like this, it will return to its original shape. And so fluid types of things can behave as elastic materials if they're treated in the correct way. And what makes Jell-O an elastic liquid material is the presence of large proteins that actually hold the thing together. That's what provides it the elastic integrity, and that basically holds the water in place and helps impart a certain elastic tendency to the Jell-O. Now, if we come back to the Jell-O and we watch it swinging back and forth, I want you to watch it very, very closely because it demonstrates something important about fluids, however. Now, if I move this back and forth, like so, you can see there's a deformation of the Jell-O that goes back and forth like this, like so. Let's do this again. We set it in motion like this, and the deformation of the Jell-O is looking like this. If we illustrate that on a piece of paper, we can take an object, in this case our piece of Jell-O, and when we move it back and forth like so, we are subjecting that block to what's called a shear force. So when we move it, when it moves this way, we're deforming it by shifting it this way, and when we shift it this other way, we're deforming it by shifting it the other way over here. And this kind of motion is called shear. It's an intuitively a clear word. If you move these two elements back and forth with respect to one another, that's what gives you the change of shape, and that is a shear type movement that is deforming this. Now, when you look at the behavior of fluids, this tendency to shear is an extremely important aspect of how fluids behave. And if we look at how fluids interact with a surface, for example, we have a solid surface here and we have a fluid that is flowing past the surface, and we can represent the fluid as if it was a number of parcels that are stacked up with respect to one another. And when we look at how that parcel is going to flow, this parcel close to the surface is not going to flow at all. That's something called the no-slip condition. This parcel up here is going to flow at a quite substantial velocity, and if you look at all the parcels in between, you'll find that they will tend to diminish in velocity and hence momentum as you go closer to the surface. And if you connect all these dots right here, you'll get something called a boundary layer. And the boundary layer is simply a distribution of fluid velocity over near an object. And the characteristic of the boundary layer is that within the boundary layer, there's a great deal of shear interaction between these different parcels of fluid. If you look at this parcel here, this is going faster than this parcel is here, and there's going to be a shear force that is going to be operating between those two parcels, and that shear force is going to set up fluid friction inside that boundary layer, and the end result is you will get a transfer of momentum from this layer up here down through here. But shear is the major thing that is controlling the transfer of momentum. Now, this tendency to transfer momentum through these shearing motions goes by a special name in fluids. It's called the viscosity. And viscosity is simply a measure of how hard it is to get fluids to move. What it characterizes at base is the ability of one layer of liquid to transfer momentum to an adjacent layer of liquid over which it's shearing. Now, you can demonstrate viscosity quite nicely. It's something you can demonstrate in your house with some fairly simple fluids. We're going to do that now. We're going to turn over here to an apparatus that I've put together here. This is a syringe and with a drain right here. And what we're going to do with this syringe is we're going to put in different liquids, and we're going to measure how long it takes to drain down into this tub down here. And so what we're going to do is we're going to start with water, and we're going to drop a little water in here, like so. And what I want to do is I want to be able to time how long that's going to take. So I'm going to get my iPod stopwatch up here and see what happens. And we're going to fill this syringe with water now, up to 20 milliliters. And when I take my finger away, that water is going to drain out of the syringe, and it's going to take a certain amount of time to do that. So we'll do that right now. Start. Now it drains more slowly as it drains down because we're losing pressure head there, but it took about 12.7 seconds for that water, that 20 mils of water, to drain through that syringe. All right, now every Sunday morning the Turner family has pancakes, and so we are familiar with applied viscosity, and you probably are too. You can take the syringe and you can fill it with 20 mils of maple syrup. Actually, this is mostly corn syrup, the way these things are put together now. And we will measure how long it takes that to drain. All right, and we're going to do that right now. Okay. Well, you can see it's going to take quite a long time for that maple syrup to be able to drain. The main thing is that the maple syrup is more viscous than the water is, and because it's more viscous, it's harder to get that maple syrup to squeeze through this narrow nozzle right here. When that liquid flows through that narrow nozzle, it's subject to a great deal of shear forces, and because maple syrup is more viscous, it's harder to get it to move under shear than water is, and it's going to take much longer to be able to for this syrup to drain. All right, so we're going to let that keep going. We're going to continue timing it, and we're going to get an idea of or illustration of the nature of viscosity there. All right, now let's have a look at some aspects of how you characterize viscosity. The principal tool that you can use to characterize the viscosity of something is to plot two quantities, the shear stress. Oops, let's open the... The thing you do is you plot two quantities. On the y-axis, you plot something called shear stress, and that is simply the force that is being exerted to cause that fluid to shear against the shear rate. And when you're talking about a fluid that is not very viscous, you are talking about a fluid that can, that a very small shear stress can produce a very large shear rate. So if we wanted to look at a fluid that is not very viscous, we would have a shallow curve right there. So we will characterize that as not very viscous. On the other hand, if you have a fluid that requires a great deal of force to get it to move at a shear rate, that's going to be represented in a steeper curve of shear stress versus shear rate. And this is going to be our more viscous solution over here. And how are we there? And so if you look at how you can characterize different fluids of different viscosities, then the shear stress shear rate curve is crucial to be able to do that. It is in fact analogous to the stress strain curve that you can use for elastic materials. Okay, our maple syrup is still draining. It's 2 minutes and 45 seconds now, and it's gone down about half. So let's continue our discussion of different kinds of materials. Now, so far, we've been treating materials as being either elastic or viscous, that is, being either solid materials or liquid or fluid materials, but most biological materials actually fall somewhere in between there. They comprise a group of materials known as viscoelastic materials, and when we say viscoelastic, we are really characterizing the nature of these materials as being somewhere in between viscous fluids and elastic solids. And it turns out that Jell-O is actually a very good example of a viscoelastic substance. If we come down here to our Jell-O blob again, we can see that it behaves essentially as a solid, as we described before. We can shake it back and forth. It behaves as an elastic material. It retains its shape. But in fact, it only does that because we're not subjecting it to a great deal of shear stress. The shear stress we're subjecting it to is just that imposed by the mass of the Jell-O itself. But in fact, Jell-O is a viscoelastic material, as are most gelatins. If you put enough shear stress on it, you will get it to flow just like a fluid. And we're going to demonstrate this with this device right here. What I did last night when I was putting together my my Jell-O blob over here. I also took some Jell-O and put it into a syringe and set it into the refrigerator to set, just like our blob over here. But because it's in a syringe, we can now subject it to a pressure, and down here at the nozzle, that pressure is going to produce a certain shear stress that, if it's high enough, will get that Jell-O to flow. All right, so we're going to come down here and we're going to subject it. We're going to compare this with our Jell-O blob over here, and we're going to put force on this, and you can see that if you squeeze it enough, it'll squirt out just like so. All right, now when you do that, you are putting sufficient stress on there to actually break down the protein interactions that are holding this together as a relatively solid material. And when you do that, those proteins can flow past one another, and when they flow past one another, they're behaving as if they were a fluid rather than a solid. If the shear stress is not quite so great, those adherent forces will tend to hold it together as an elastic solid, and it will tend to retain its shape. Now, Jell-O is a fairly simple example of a viscoelastic material. But if you look at a viscoelastic material, how it might behave on our shear stress shear rate curve, we see that it's going to behave something like the way that we've seen for biological materials that are more elastic in nature. So if we draw our shear stress shear rate curve, we can say that there are going to be regions where it's going to be, you're going to get very little shear rate for a lot of shear stress, but there's going to be some point at which a small increment of shear stress is going to make that behave as a fluid. That is, down here, the shear is it's going to be hard to get that material to flow, but when you get it up into this region, it's going to be easier to flow. And that's what's happening with our jello shooting out of the syringe. Now, biological materials often behave this way, and the fact that you have different kinds of behaviors based upon the rate at which you can shear these things leads to some interesting features of locomotion. So, for example, if you take a snail, and the snail is basically a long foot with a shell on it, and of course it has little antennae up here. And that snail can crawl along on the surface, even just a very smooth glass surface. And of course, one of the interesting questions one can ask is, how is it that it manages to do this? Well, it turns out that the snail secretes a mucus, which is a typical viscoelastic material, onto the surface of the glass, and that mucus behaves differently under different kinds of shear rates. If you look closely at the foot of a snail, you'll see that there are little waves of contraction that pass along the length of the snail's foot, like so. And if those are in a viscoelastic layer of mucus, these are traveling backwards at a certain rate. And when these waves of peristaltic contraction producing these ridges achieve a certain rate of movement, it's imposing a shear stress on this mucus. And at that rate of shear stress, it behaves essentially as a solid material. But of course, at the meantime, you have a forward motion of the snail's foot, and the forward motion is slower than the rate at which these ridges, these peristaltic ridges, go back to the back. And at that rate, the mucus acts in a more liquid manner. And so when the peristaltic waves are going back, it's as if it's pushing against a relatively viscous fluid, but the viscous interactions at the foot that might be impeding the forward motion, that's taking place at a lower shear rate and effectively a lower viscosity than is being experienced by the ridges. And in that way, the snail can move forward. And if you're interested in seeing how this works, next time you're in your garden and you get a snail out there, just plunk it on a piece of glass, and you can see these peristaltic waves of motion pushing backwards on the foot and hence pushing the snail forward. Okay, well, back to our maple syrup. We see over here that it's been 9 minutes and 30 seconds right now, and it's taken about that long for that stuff to drain. And this is a fairly dramatic illustration of how viscosity affects the flow of materials through small tubes. Okay, well, that's all for now, and we will see you another time. Good day.